Assalamualaikum and have a very good day to everyone. First and foremost, I would like to express my gratitude to the third International Conference on Education, Social Sciences and Engineering of 2022. I, Muhammad Afiq bin Shekman, is the presenter and the first author. The second author is Associate Professor Muhammad Ibrahim Syafiai, and both of us are from Center for Artificial Intelligence and Robotics ICOSA, MJIIT, Universiti Teknologi Malaysia, Kuala Lumpur. The title of the paper today is EEG to Brain Topography Classification using Convolutional Neural Networks. Let's have a look at the presentation plan. We will first go through the introduction, in which there is background, problem statement, aim and objectives, and gloss through the literature review, dive into the methodology, and then have a look at the results and discussion before ending it with conclusion and recommendation. Without further ado, let's begin. Electroencephalography or EEG is the most preferred technology for brain-computer interface over other BCI modalities. Why is it so? It is because EEG is more commonly used due to its high temporal resolution, affordability, availability, and portability. EEG has been known to produce noisy and non-stationary signals that would actually degrade and cause poor performance in BCI applications. As such, common spatial patterns or CSP is the primary choice to process multi-channel motor imagery signals. This is because of its ability to produce discriminative features that is useful to the classifiers. It does this by generating a set of spatial filters that can define multi-dimensional data as a set of uncorrelated components. In this manner, CSP can be used as a feature extraction method that can be before the classifier. Typically, the classifier can be a machine learning based, but more recently, CNNs or deep learning in the form of CNNs have been gaining traction over the years. This is because of their capability to perform automatic feature extraction and the convolutional layers present in their architecture that are useful in taking in sparse features. The rise of deep learning is becoming more and more common and replacing many traditional classifier methods in the medical field, with more of these CNN-based architecture being utilized as classifiers. Nonetheless, in order to process these EEG signals as inputs to CNNs, many researchers have been trying to take in EEG signals directly as inputs to CNNs, but with additional preprocessing required in order to make the signals, which are really time series, fit as CNN inputs. Other works attempt to translate EEG signals into images by filtering and CSP. Afterwards, they would apply temporal, depthwise, and separable convolutions in which the output can be converted to image representations. Another work utilizes short-time Fourier transform, which can later be rendered as spectrum images. However, these methods currently do not convert the EEG signals into images that can be direct brain representations and may leave out other important features such as brain connectivity. As such, the aim of the study is to investigate the novel combination of CSP algorithm and topography plotting, in which we convert signals to topography imageries for CNN inputs. And then we proceed to validate the performance of the approach on two different networks, namely basic CNNs and pre-trained CNNs. Let's gloss through the literature review. For EEG and CSP, it is known that EEG has the non-stationary and non-linear features, and that there are noises present in the EEG signals that needed to be filtered out. There are also three typical types of filtering utilized for EEG signals, namely the spectral filtering and temporal filtering, and the last one is spatial filtering, which is where CSP is the dominant method of choice to be utilized as the pre-processing method. As such, you can see here that CSP is being used for a lot of applications in motor imagery classification, for instance, in processing multi-channel motor imagery signals, and also in the 2008 paper of Blankets, in which it shows the ability of CSP to produce discriminative features. Last but not least, we look at CNN as classifiers for CSP-based methods. However, with the interest of the inputs utilized as the preprocessing of inputs into the CNNs. As you can see here, while all of them are using similar forms of CNN, they were using different pre-processing techniques, either either using temporal, depth and separable convolutions, or just short time Fourier transform alone, or a combination of CSP and STFT. With that, let's dive into the methodology. Overall, as you can see, this is the overview of the system, in which we pass the data set and we do the pre-processing, in which the pre-processing we perform the common spatial pattern in which the features are extracted, and then by these extracted features we plot a topo map, and the output of this topo map is the topography images that will be passed into either CNN or pre-trained CNN, and for classification purpose. And below is the architecture of the CNN used in the study. The first one is the basic CNN, and the second one is the pre-trained CNN utilizing MobileNet V2 architecture. As for the data itself, we were using the BCI competition tree set 4A, and only the second data set is used for the study. The second data set consists of 118 channels, and they are recorded from healthy subjects sitting on a comfortable chair with arms resting on their armrest, and they were looking at the images of arrows and instructions from the computer screen. And typically there are two classes, which is namely the right hand and foot, and these are generated for all the 5 subjects here. As you can see, there are subjects AA, AL, AV, AW, and AY, and however with varying number of trials, with AA having the most number of trials. Let's have a look at the architecture of the CNNs. So for the first basic CNNs, the main architecture here is the convolutional and max pool layers stacked 2 times over each other, and the convolutional layer topped with flattened and dense layers to get the classification outputs. For the pre-trained CNNs, what we get here is the pre-trained weights from the MobileNet V2, which is generally consisting of a pointwise convolution, depth convolution, and another pointwise convolution. And then we remove the final dense layer and replace it with additional average pooling, flattened, and dense layers. So at the input of this MobileNet and basic CNN, we apply the data set that has been converted into topographic images. This is achieved by using the MNE Python package that converts the raw filtered data into an image that we can save for each trial, for each subject. The experimental setup is as shown here. Our classification model is built by using TensorFlow. We use a training test split of 0.2, and we feed into our model a batch size of 8 for 75 epochs with a learning rate of 0.001. For one completed epoch, it took on average 50 steps for the entire dataset to pass forward and backward through the neural network. We apply standardization, and we applied a constant 0.3 dropout rate throughout the layers. The performance index that is mainly used is the mean square error, which can be seen here as follows. It is the summation of the number of predictions, vector of n predictions, of the squared vector of n predictions, minus the vector of observed values corresponding to the inputs to the function, divided by the number of n predictions. Let's have a look at the results and discussion. Here, as you can see, we are training the architectures proposed as a binary classification problem, and these are the following results. For the subjects AA, AL, AV, AW, and AY, for subjects AA, AL, and AW, the results are very great. For basic CNN, we roughly got about 50 to 70% for basic CNN, and roughly the results are on average 63%. for training error and 43% for the classification accuracy. And for mobile net, we have a much better training accuracy of 84%. However, the classification error accuracy does not improve that much with only 63%. This is weighted more due to the classification error of AA and AW and AL, which do not improve greatly. Let's have a look at the images used to compute the model accuracy then. Here, as you can see, is the test images used in the model prediction. A is the correctly classified image and B is the wrongly classified image. As you can see, it is this is the similar case. While this is only a sample size of 2, a similar situation can be seen for other test images. It is not easy even for the human inspector to be able to discern between what is a left-hand signal and what is a foot signal. As such, we believe that much less useful features are in the current technique that we were using, and we believe that we need to select a different technique, select a more effective technique, such as more effective CSP that can include in more useful features. So to conclude the study, as mentioned earlier, we have been able to prove that it is feasible to convert the EEG signals to brain topo maps, and then we can apply the CNN classifiers to the topographic images. However, the average performance is only about 60% compared to similar works. In order to improve the performance in the future, we need to be able to utilize better brain representation strategies and better feature extraction strategies. As such, besides that, with the images of better CNN architectures and paradigms such as attention model, transformer, and future short learning, these architectures and paradigms can also be considered in future investigations to be used as classifiers. That is all for today's presentation. I would like to thank you again to the ICESE 2022 and for all of you who has spent time to go through this presentation. Have a nice day.